The formulas for electron mass and wavelength given in video 4 suggest that the electron is an event that oscillates between an electrical wave state, duration 10 to the 23 units of Planck time, to a mass point state, duration 1 unit of Planck time. This also suggests that the simulation clock rate is the origin of Planck time. This would be akin to running a loop where every increment to the counter age creates a unit of Planck time. The electron, therefore, does not exist at any one unit of time. Rather, it is an event that oscillates over time. We may consider time as one of the dimensions of the electron, for which we would require 10 to the 23 increments to variable age to create one electron event. If the electric state is a wave state and the mass state is a point state, then only in the mass state does the electron have defined coordinates within the universe hypersphere. And so if we could stop time, our solid planet Earth would disappear. Instead, we would see a number of points within a defined region of space, but most of the particles that comprise our Earth would be as waves, such that for every electron in a point state, which we could see, there would be 10 to the 23 electrons as waves that we couldn't see. At the next increment to the simulation clock, aka the next unit of time, there would be a different set of particles in the point state, as particles oscillate between wave and point. But these points too would be confined to that region of space we call planet Earth. If we could record 10 to the 23 frames and play at high speed, we would see a solid planet Earth. And so our solid Earth is actually a solid Earth per second. The reason it seems solid to me is because I inhabit a human body per second. I too do not exist at any one unit of time. Instead, I am the averaging of events occurring over time. Where is this taking us? Gravity at the Planck scale cannot operate between the Earth and the Moon if there is no Earth and Moon at the Planck scale. So let us forget gravity for now and look at the universe as a series of mass points. Some are clumped together, suggesting planets, but that doesn't concern us. Now we connect every particle mass point in our universe to every other particle mass point directly to form a universe-wide network of particle-to-particle pairs. If we have 3 particles, then we have 3 pairs. If we have 4 particles, then we have 6 pairs, and so on. We will then rotate them so we can call them orbitals, and because they're between mass points, they can be gravitational orbital pairs. As mentioned in the previous video, the universe expands at the speed of light at c and pulls particles with it at c. And so what we then find is that these orbital pairs all rotate at c. And because we're working in discrete units of time, we can say that each orbital rotates 1 unit of Planck length per unit of Planck time. The universe clock ticks and they rotate again. And so we have this in-body, universe-wide network of orbital pairs rotating at the speed of light in hypersphere coordinates. We notice that the Moon does not orbit the Earth, but rather both planets orbit around a center point called the barycenter, which is near the Earth's surface. But when our high school teacher calculates gravity, he or she doesn't use this barycenter. Instead, it's used the distance from the center of the Earth to the center of the Moon. In this orbital model, there is no Earth-Moon barycenter because at the Planck scale, there is no Earth-Moon. Particles are just orbiting each other. It is only when we sum all these discrete orbital rotations and average them over time that we will see moons orbiting planets and planets orbiting stars. If all the orbitals between a satellite and the Earth are aligned in the same direction, then the satellite will follow a circular orbit around the Earth. If all the orbitals are unaligned, then the satellite will follow a straight line orbit. We call straight line orbits falling. As a simplistic analogy, if there was a hole through the center of the Earth, the satellite would fall through it to the other side of the Earth and then fall back. In other words, it is a straight line orbit. However, what we see in practice is the satellite hit the Earth, thus transferring its orbital momentum to the Earth. The satellite is now in a new orbit, an Earth surface orbit. The degree of orbital alignment, therefore, determines the type of orbit, circular, elliptical, or straight line. In science, there is a gravitational coupling constant. This measures the strength of gravity, and we find that gravity is very weak compared to other forces. But in this model, we simply invert this coupling constant, and we find that gravity is actually stronger than the electric force. However, it seldom occurs. To have any two electrons simultaneously in the mass state occurs only once every few seconds. And as our observed orbits are averaged over time, gravity therefore seems weak. I noted that orbits occur at the speed of light, but we can see clearly that they don't. Orbital speed depends on distance. And even at close distance, speed is relatively slower than c. But this is our measurement in 3D space. And referring back to the video on relativity, the satellite is orbiting the Earth's timeline axis, which is traveling at c. But along the horizontal 3D space axis, the orbit slows according to our principal constant alpha, the fine structure constant. This alpha gives us the ratio between 3D space and hypersphere coordinates. It applies to both. One reason why it is so confusing, it applies to hypersphere geometry. This means that regardless of distance between the satellite and the Earth, the orbital speed equals c equals 1 Planck length per Planck time. But this is distributed between 3D space and the hypersphere timeline axis. We can use our relativity formulas to translate between the two coordinate systems. These gravitational orbitals occur between two particles in the mass state. However, particles oscillate between the mass state and the wave state. Whilst in the wave state, our orbitals now resemble atomic orbitals. And indeed, we can use the same formulas for atomic orbitals, and we look at this in the next video. I have put the formulas used with examples on this wiki site.